Okay, so let's talk a little bit about TE and TM wave characteristics. So if you look at the solutions for the TE and TM waves, there are several things that they have in common. First of all, in the x direction, which is the direction between the plates, you can see that E and H will have a sinusoidal standing wave distribution. You can also see that any plane, any xy plane, which is planes that are perpendicular to the direction of propagation, will basically have equal phase. And so in other words, TE and TM waves are plane waves with surfaces of constant phase given by z equal a constant. But of course, they do not have constant magnitude. And then finally, the surfaces of equal phase are going to propagate along the waveguide with a velocity equal to the phase velocity, which is omega over beta. And beta will be beta in the guide. So if we now look at E in the time domain, this is what E in the time domain looks like. And what I want to point out here is that this cosine of omega t minus beta z comes from e to the minus gamma z when we add the time dependence in and take the real part. And notice that the only way we're going to get propagation is if gamma is equal to j beta. So, or is imaginary. So let's look at what gamma actually is. And this is gamma in the guide. That's what the line represents. So gamma is the square root of h squared plus j beta squared. And if we substitute in for h and we substitute in for j beta, we get the following expression for gamma. And so you will notice that gamma is mode dependent and it's also frequency dependent. So this is the difference. When we first started talking waveguides, we were talking about the bar over gamma. This is the difference between gamma with the bar, is that it has this factor in it that's dependent on properties of the waveguide or the mode number. So notice A and M. Also notice that for certain values, for a given M, for certain values of omega, the term under the radical will be 0 or less, making gamma imaginary and meaning that we can have propagation. The frequency at which this occurs is referred to as the cutoff frequency. And if the frequency goes below the cutoff frequency, then gamma becomes real, meaning we don't have propagation, we have attenuation. So this is known as the cutoff frequency, and what it means is that at a given mode number, waves may or may not propagate down the waveguide depending on the dimensions of the waveguide, A, and omega, the frequency of the wave. So the cutoff frequency, once again, is the frequency below which propagation will not occur, and it is mode dependent. And so we can get a solution for the cutoff frequency in terms of hertz. It's basically equal to m over 2a times the square root of mu epsilon. So obviously higher modes will have a higher cutoff frequency. And then lambda, the wavelength, is basically 2a over m. Now, when f is greater than the critical frequency, then our gamma becomes purely imaginary and propagation will occur. And basically then gamma becomes equal to j beta, which could be expressed in terms of the cutoff frequency and the frequency of the propagating wave. So since the frequency of the propagating wave is always is always greater than the cutoff frequency, then this term is always less than 1, meaning you have j beta times this factor, which is kind of like the waveguide factor. So when f is below the cutoff frequency and gamma is real, then what happens is the wave becomes an evanescent wave. So it is attenuated as it propagates into the guide. And we could express that with this expression. So previously, if the wave was propagating, we didn't have an alpha, we had a j beta. And when we added the e to the j omega t and took the real part, we got cosine of omega t minus beta z. In this case, e to the minus alpha z is a real number. It's not a complex number. And so when we add the e to the j omega t and take the real part, this just remains as an attenuation factor. So in the case where the frequency is below the cutoff frequency, or and I say critical frequency here, but I mean cutoff frequency. When it's below the cutoff frequency and gamma is real, we have what's referred to as an evanescent wave, and it will not propagate down the waveguide. So another thing to notice is that the wavelength and the phase velocity are actually different in the waveguide than they would be in an unbounded media, and they're also mode dependent. So we can calculate the waveguide by taking 2 pi over beta. We can calculate the wavelength by taking 2 pi over beta m, and we can calculate the phase velocity by taking omega over beta m, where beta m is this modified beta because of the properties, because of the waveguide properties or the waveguide factor. So it's actually the phase velocity divided by this factor because of the presence of the waveguide, where the phase velocity here is what the phase velocity would be if this same wave in the same dielectric were propagating in an unbounded media. So notice that the phase velocity is mode dependent, and it's also different by this factor. Okay, in the next lecture, we will look at an example problem, or I guess actually there's time we can look at it right here. This hasn't gone too long. So basically, this is an example that just illustrates the cutoff frequencies for different modes propagating within a waveguide, and we put some numbers in here. So here's 1.25 centimeters. That would be the plate separation. And we're given the phase velocity at 15. We would like to find the phase velocities at 15 gigahertz and the lowest modes that can propagate at 25 gigahertz, as well as the cutoff frequencies. So the first thing we have to do is calculate the cutoff frequencies, and we see that as a function of m, we can basically express the cutoff frequency as a function of m. So basically plugging in everything, then the cutoff frequency is going to be 12 times m gigahertz. And I believe there's a table. I guess not. Okay. So basically you plug in values of m. So m can be 0, 1, 2. So basically you would have 12 gigahertz and 24 gigahertz respectively for the mode numbers 1 and 2. And notice that for the TM0, that's basically the TEM mode. We plug in 0 and we get 0 gigahertz for the cutoff frequency, meaning that all TEM modes will propagate down the sky. No TE modes exist because, as we said back when we talked about TE waves, if you substitute 0 in for the mode number, you don't have a TE mode. All right, so for the TM0 mode, the phase velocity in the guide is equal to the normal phase velocity. So we take the phase velocity in the guide, and the normal phase velocity is equal to c. So we take the phase velocity in the guide, which is c, divided by the guide factor, and then for higher order modes. And so for higher order modes, we would use the correct f sub c. So if we have mode 1, we use fc1. We plug all of that in, and we find that the phase velocity is 5/3 times the c. So for the TM0 mode, that's basically the TEM mode. And the TEM mode doesn't even notice the waveguide is there. So it's like it may as well be propagating in free space because the phase velocity is equal to, in air, the speed of light. For the mode 1, notice that the phase velocity is now 5/3 of c. So notice that that's greater than the speed of light, which is kind of an interesting phenomenon. Now what we need to understand is that this is only the velocity of the phase fronts. It's not the velocity of actually the wave energy. So we're actually not propagating anything at faster than the speed of light. It's just a consequence of what happens with the phase front in the waveguide. Okay, at 15 gigahertz, TE2 and TM2, so the second mode would not propagate at 15 gigahertz. We would have to have 24 gigahertz, so we're below cutoff and we won't propagate. Now the lowest order mode that can't propagate in this waveguide would be the third order mode, because the third order mode would be 36 gigahertz, and because because that would be then cut off. So the third order mode would need to be 36 gigahertz to propagate. So at 25 gigahertz, we will not propagate down the waveguide.